Greetings everybody, I'm Preetham and my project is all about reinforcement learning in PacMan. So today we're going to be discussing about the problem statement, introduction to reinforcement learning and deep Q learning, neural network, epsilon greedy strategy, hyperparameter explanations, training, results, and the video. So the problem statement. Given to us is a Pac-Man game. The game consists of a maze with pellets scattered around and ghosts which chase the main player, which is the Pac-Man. The objective of the game is to acquire all pellets without running into the ghosts. Some special pills called energizers allow the main player to attack and kill the ghost for a small duration. The agent has 3 lives and our objective is to make a player bot, an AI bot, that can successfully navigate this maze, collecting as many pellets as possible in one game. Initially, the expectation was that we would try to complete at least one level. However, later in the project, we will be aiming to try and score as many points as possible in a 1600 episode average. So, reinforcement learning. Reinforcement learning is a branch of machine learning which is different from supervised and unsupervised learning as it requires no dataset for training. It is simply a computational approach where an agent interacts with an environment by taking actions in which it tries to maximize an accumulated reward. Here it is a simple graph which I will be referring. An agent in a current state, which is S, takes an action A to which an environment reacts and responds, returning a new state and reward to the agent. Given the updated state and reward, the agent chooses the next action and the loop repeats until the environment is solved or terminated. The reinforcement learning comprises of two constant components that keeps changing with every step. Agent is the thing that takes an active role by implementing different actions. Environment is some model of the world which is external to the agent. It provides the agent with the observation based on which the agent takes action and gets a reward for its action. The environment changes the state of the agent based on the action taken by the agent. Our agent's goal is to find a set of actions that would maximize the overall reward. A neural network consists of several connected units called nodes. These are the smallest part of the neural network and act as the neurons in the human brain. When a neuron receives a signal, it triggers a process. This signal is passed from one neuron to another based on the input received. A complex network is formed that learns from the feedback. The nodes are grouped into layers. A task is solved by processing the various layers between the input and output layers. The greater the number of layers to be processed, the deeper the network. Therefore, the name deep learning. Deep learning uses neural networks that are trained using the stochastic gradient descent optimization algorithm. The DQN neural network model is a regression model which typically will output values for each of our possible actions. These values will be continuous float values and they are directly our Q values. As we engage in the environment, we will do a predict to figure out our next move. When we do a predict, we will get three float values, which are our Q values that map to the actions. We will then do an argmax on these like we would do with our Q table values. We will then update our network by doing a fit based on the updated Q values. CNN takes in-game screen images and outputs the probabilities of each of the actions or Q values. To acquire a tensor of probabilities, we do not include any activation function in the final layer. As Q-learning requires us to have knowledge of both the current and next states, we need to start with the data generation. We feed pre-processed input images of the game space representing the initial states S into the network and acquire the initial probability distribution of actions or Q values. Before training, these values will appear random and suboptimal. With our tensor of probabilities, we will then select the action with the current highest probability using argmax function and use it to build an epsilon greedy policy. Next, we define a function called epsilon greedy for performing epsilon greedy policy. In epsilon greedy policy, we either select the best action with probability 1 minus epsilon or a random action with probability epsilon. We use decaying epsilon greedy policy where the value of epsilon will be decaying over time as we don't want to explore forever. So our policy will be exploiting only good actions. We store all the agent's experience, that is state, action, rewards, in the experience replay buffer and we sample from this mini batch of experience for generating the y values for the update function and hence then train the network. Next, we'll discuss the hyperparameters. The discount factor notifies the AI about how far it is from the destination. This typically is specified by the developer of the algorithm that would be installed in the AI. The learning rate is a hyperparameter that controls how much to change the model in response to the estimated error each time the model weights are updated. Choosing the learning rate is a challenging value as a too small value may result in a long training process that could get stuck, whereas a value too large may result in learning a suboptimal set of weights too fast or an unstable training process. The learning rate may be the most important hyperparameter when configuring your neural network. Therefore, it is vital to know how we investigate the effects of the learning rate on model performance and to build an intuition about the dynamics of the learning rate on a model behavior. Allowing the agent to learn from earlier memories can speed up learning and break undesirable temporal correlations. Reinforcement learning algorithms use replay buffers to store trajectories of experience when executing a policy in an environment. During training, replay buffers are queried for a set of trajectories, which can be either sequential subset or a sample, to replay the agent's experience. So, to sum up, we are ready for the training. First, we pre-process and feed the game screen to our DQN, which will return the Q values of all possible actions in the state. For each epoch, we feed an input image in our network to generate a probability distribution of the available actions before using an epsilon greedy policy to select the next action. We then input this into the gym environment and obtain information on the next state and accompanying rewards and store this in our buffer. After a buffer is large enough, we sample the next states into our network in order to obtain the next action. We also calculate the next reward by discounting the current one. We generate our target Y values through the Q-learning update function and train our network. Next, we sample some random batches of transitions from the replay buffer and calculate the loss. By minimizing the training loss, we update the network weight parameters to output improved state action values for the next policy. Once the training has finished, we can evaluate the performance of our agent through the graph, which is obtained statistically. So this is the graph which I obtained for after executing the program for 250 episodes. And this is the graph which I obtained after training the agent for 1600 episodes. This is a demo of the best run of the simulation. So in the end, I would like to conclude by saying that this project evaluates the effectiveness of deep Q learning applied to PacMan. This presentation explains the DQN reinforcement learning techniques and describes how these techniques were combined to create a model capable of learning to play PacMan. This model, after training approximately for 1200 episodes, wins around 95% of the games. Therefore, it could be concluded by saying that deep Q learning is able to successfully clear a game of Pac-Man. Thank you.